Okay, now we're going to do a couple of additional problems using this geometric technique. Okay, this particular problem is the object function is torque, which we'll give by capital T, and that torque, which is in units of Newton meters, is developed by an internal combustion engine, and we find that it is represented by an equation that has two terms associated with it, two parts, wherein the omega is the rotational speed of the combustion engine, and that's in radians per second. And so the radians per second is the speed, and once we put in radians per second for the two terms, then all of the other constants and all of the units are associated with that, such that the answer would be torque in Newton meters. And so in this particular case, we want to determine the maximum power at which this engine is capable and the rotative speed at which the maximum occurs. And so we'll find that the maximum power is simply the torque times the rotational speed. And so we're trying to maximize that term as a function of the rotational speed. And so, as I said, in a rotating type of system, torque times the rotational speed can be shown to be related to the power. Okay, and again, power would be in watts, and we see that the torque is in Newton meters, and then this omega would be in rads per second, and so we then would have Newton meters per second, and a Newton meter per second ends up being related to the power term that we are after, because a Newton meter corresponds to a joule, and a joule per second is a power watts. And so by multiplying that equation that we had before here by another omega, we then have that power is equal to the constant times omega to the 1.7 instead of 0.7 minus 3.74 to omega to the second power. And again, because instead of the single power, it's now to the square of the rotational speed. Okay, so here is our equation. We are wanting to maximize the power and find at what value of omega do we obtain that maximum power. Again, we could very easily use calculus, taking the derivative of power with respect to omega, setting that equal to 0, and solving for the value of omega that provides the maximum value, and then substitute that back in for the magnitude of the power itself. But we're going to do geometric programming, and in the sense that we developed earlier, we see that the y star, which is the object function at the maximum or minimum condition, that this would be the p star, is simply the constant, the first constant, divided by w1 over to the w1 power. And the second part then gives us the negative, the constant here in the negative. This is the C2. It just happens to be negative because of the influence of that term, divided by W2 raised to the W2 power. And putting it in this particular fashion, we saw before that provides that the W's have to add up to be equal to 1. And the power times the W1, the power times the W1 have to add up to be equal to 0. So those are our two algebraic equations in terms of W1 and W2 that we could very quickly, very easily solve. And upon doing that, we see that W1 is equal to 6.667, and W2 is minus 5.667. Okay, again, they add up to 1, but one happens to be negative and the other one is a higher positive number. So unlike the problem that we did earlier, where they added up to 1 and it was 5/6 and 1/6, and we were able to say something about the terms themselves and what they have to do. The same thing holds. It's just we have this negative influence here of one of the terms, and so we could still go through the same process and say that this really represents this term divided by both of the terms together, and this term corresponds to this term divided by the two added together. And so we have our value of W1, W2. We can then, that is Y star. It's also the G star that we said before. We can put that right into our equation where we have the two values of, the two values of the C that we had before, divided by the W1 raised to the W1. Here's the C2 divided by the W2 raised to the W2 power. We can use our calculator then to determine that, and we find that in the appropriate units of watts, we see that the power is 123 kilowatts. And so that is the value of Y star. We can now use that value of Y star and the two values of W and go backwards and solve for the U star 1. Again, taking the 6.67 times the Y star and then solving this, and we find that then becomes, we can solve for W. The W at the starred condition. This is the omega at the starred condition, and we find that it is 469 rads per second, or revolutions per second, depending on how you want to look at it. So 469 rads per second then is the rotational speed at which the maximum power occurs. Okay, so again, very similar type of problem. We started off with a dependent variable that's a function of the independent variable omega. We exchanged the torque to power because that's what we were actually wanting to maximize, and so we added another power of omega. We then used the geometric programming then to calculate the value of W, the omega, that this is actually maximized, and through that process. Okay, one last problem here that kind of ties in the previous problem that we did is that we have this water flow system going through a waste treatment plant, and we have then the effluent coming out from the water here. So we have treatment, and the treatment corresponds to dilution as well as chemical action, so that this effluent meets some type of a code requirements. The size of the reactor can decrease as the dilution increases, and so if we brought in more water here, we can make this plant, the size of the plant, smaller, because the overall effect is to take the waste stream and get it down to an efficient, a lower waste effluent, so we can overfill with water and make this a little bit smaller. So we have competing effects, plus we also have the diameters associated with pumping cost and other things like that. So in this particular case, we're looking for the cost of operating the system. And so the first thing we are told is that the cost of this reactor is directly inversely proportional to the water flow rate. And so if we have more water going in, we recognize that the plant itself doesn't have to be as big, and so its cost is going to be smaller. So we have that term for the cost of this treatment plant or this reactor. Q is in cubic meters per second. Okay, the equation that we for the pumping costs is broken down into a term very similar to what we saw before, and as you see, it's related to the square of the flow rate, of the volumetric flow rate, divided by the diameter to the fifth. And so this is similar to what we saw in terms of the lifetime pumping costs. The fifth power comes into play because of the velocity and the friction of the pipes and that type of thing. So we have that particular term as part of our optimize our total system cost. And so what we then have is we have now three terms in our object function. We have the cost of the pipe, and that's the same as what we had before, 160 times the diameter raised to the diameter to the millimeter size. And that's our cost. That's the first cost of the pipe. This is our cost associated with the lifetime pumping cost. And now we see not only is it a function of the diameter of the pipe as we saw before, but the flow rate of the water going through the pipe. And so in essence, that Q square then gives us a different point on the Moody-Darcy friction factor. And so a different friction factor, different Reynolds number through the system. And so we had to combine all of that together instead of just having a single flow rate through. And so we now have this second term, which is the lifetime cost of operating or flowing the water, now a function of D as well as Q. And so in this particular problem, both D and Q can be manipulated. So this is a two-dimensional problem such that the two independent parameters are diameter. We can select our diameter, and we can also select our flow rate. And so the last term here, the 150 over Q, was related to the cost of the plant itself. So we have pipe, and we have the plant itself, and then we have the operating cost due to the flow and the size of the piping. So we now have an object function that has the first variable influence, both variables an influence, and then the second variable's influence. And so as before, we write it in the fashion. We now introduce three W's because we have three terms. Okay, our first term here in this product sequence is the constant, the C1 here, and our W that we put in, that is the W that we have selected for that first term. Okay, we now have the second term, and the constant in the second term is this 220 times 10 to the 15th. And then it's divided by the second W, which is W2, and that is raised to the W2 as part of the product sequence. And then finally we have this term here, which is the constant C3 divided by the W3 raised to the W3. So in the spirit of the geometric programming, we see that we have the three components. Now, this particular equation is then subjected to these two conditions. And the first condition is that W1 plus W2 plus W3 has to be equal to 1. And now the other condition corresponds to what we had before, but now we have two independent variables. And so unlike before, now we have to write that other equation in terms of each of the independent variables. And so it gives us two additional equations. And so when we look at this, this equation right here, and just think of the d, the influence of the d. Well, in the influence of the d, the first term has a d to the first power. And so what we said was the A1 is then times W1. So this term here comes about due to this term having a first power dependency on the D. We then look at the second term and we see that the D is a minus fifth power. And so that's where we get the minus 5 W2. And then we say the third term doesn't have any D associated with it. And so there is no third term then in this equation. And we set that equal to 0. Now we go back and we look at, for the next independent variable, Q, we do the same thing. The first term doesn't have any Q associated with it. And so there's no term here with respect to W1. We go into the second term, and it does have a square dependency on Q. And so that's where the 2 comes about times W2. And then finally, we look at this last term that does have a Q dependency to the minus 1, and that's where we get the minus W3. And so now in this two-dimensional problem, we see that we have these three equations in three unknowns. And so we have a linear equation set that we now can solve however you want to, by substitution, by matrix method, by guess and check. But now we have these three equations and three unknowns that we can solve. And upon solving them, we see now that W1 is 5/8, W2 is 1/8, and W3 is 2/8. And so we can now, because these add up to 1, we could go back and say that at the optimum condition, this term right here is going to be 5/8 of the solution. The next term is going to be 1/8 of the solution, and the final term is 2/8 of the solution. And so that's, we see that relationship. And so with that in mind, we can put those W's in, and into this equation here, W1, W2, and W3. And we could then solve, again with our calculator, and we find that the cost, which consists of the plant cost, the first pipe cost, and the operating cost, is $30,224. That is the answer to the problem. And now we need to independently go back to each of the U stars, and we said, well, of this object function, 5/8 of that object function was equal to the first term in terms of D. And so we can then use that to solve for the D star, which is 118. We then look at whichever is the simplest to solve, and we see that the third term, which is only a function of Q, is the next easiest to solve. And we know that that is 2/8 of the object function. And so 2/8 times the object function then can be back solved for the value of Q, and the value of Q star then is this flow rate. And so we can stop at that point. If we wanted to, we could go and check if 1/8 times this is equal to this part. We can put in that Q star and that D star and see if this term, this part of the three terms, is indeed equal to 1/8 of the object function. And you would find that it is. And so this then is the solution to that problem. And so at this particular point, I'm going to go ahead and stop. Our next section that we'll briefly talk about is how do we handle it when we have a constraint in a geometric problem. And so we're going to look at the case where we have a polynomial or we have a multiple term equation for the object function, but now we have some additional polynomials that correspond to a constraint in the system. And we saw that early on when we set up a two-dimensional equation with a constraint, but we're going to then show how we go about doing that using this methodology.